Welcome back. Today we are talking about section 1.2, linear functions. Last lecture we were looking at 1.1, what is a function? And today we're going to get a little bit more specific, looking at the linear function. So our first definition is a linear function, specifically, is a function that describes a line. Okay, oops, gotta move that down a little bit. There we go. Okay, specifically, linear functions, these functions, can be put into a specific form. Alright, and this form is what we call the slope-intercept. So the slope-intercept form. Alright, we'll highlight that for us. And the slope-intercept form is what you might remember as our y is equal to mx plus b. That's our slope-intercept form. However, we're going to start looking at this as being our f of x. So our y values will be our f of x values now. Okay, so this is our slope-intercept form. Okay, so in our slope-intercept form, we need our slope and our intercept. Okay, so m is our slope, and b is the y-intercept, or the vertical intercept. So this is where the graph crosses the y-axis. Okay? So where the graph crosses the y-axis, and this has to happen at x is equal to 0. Okay. Now the slope refers to the rate of change of the y values with respect to the x values. Okay, so what I mean by this, what this means is we take the fraction of the change in the rise of the function over the change in the run. I'll draw a little picture of this for us. So say we have our x and y axes here, and we have a line that looks like so. This would be our y-intercept, right? Okay. And so let's pick some points here. Let's say this point is x number 1, this point is x number 2, and then the corresponding points on the y-axis. I'll get rid of my little note here about the intercept because it's in the way. Alright, here is y1, and here is y2. Okay, so our run is how much we are moving in the x direction. This is our run. And we can find this by taking the bigger value and subtracting the smaller value. Okay? And this is our rise. It's our change in our y values. So, same thing, bigger y value minus the smaller y value. Okay, so we also use the phrase change in, okay? We can write this as this little triangle symbol, which is actually the Greek letter delta. Okay, so if we wrote delta x, that means the change in x, or x2 minus x1. Those all mean the same thing, okay? So our slope, this is our m value, is our slope. We know it to be the change in y over the change in x. So the change in y over the change in x. Or we could write this as our y2 minus y1 over x2 minus x1. Okay? And this last form here, this is called the difference quotient. Difference quotient. When you subtract two things, it's called a difference, and when you are dividing, you have a quotient. So we have the difference quotient. Alright, so one more thing before we jump into this first example here. Alright, if we are given a data table, and we want to determine if the data could be from a linear function. So we need to determine if the given data could come from a linear function. We should look for constant change in y values for equal changes in x values. Alright, so now we'll jump into our first example, which is looking at these tables. Alright, so example 1 is determine whether the following tables could represent a linear function. So, part A, first we need to look for equal changes in x. Well, to go from 0 to 100, we need to add 100. To go from 100 to 200, we add 100. And to go from 200 to 300, we add 100. Okay, so that's good there. We have equal changes in x. And now our g of x, well, these are our y values. Okay, so we're looking for constant changes in g of x. So, to get from 25 to 50, we need to add 25. To get from 50 to 75, we need to add 25. And to get from 75 to 100, we also need to add 25. Alright, so this could be a linear function. We have equal changes in x and constant changes in y. Okay, let's look at part B. So part B, we go from 0 to 5, that's plus 5. Same thing from 5 to 10, and then 10 to 15 are both plus 5. Okay. Looking at our y values as our f of t values, we have 10 to 20. Okay, that looks good. We add 10. And 20 to 26, we add 6, and then 26 to 40, we add 14? That can't be right. Alright, so this is not a linear function. Alright, because there are not equal changes in y. I'll say in the f of t values. Alright, we have plus 10, plus 6, and plus 14. They're not constant changes in y. Okay, and then for part C, it looks like we're adding 12 each time for our x values. That looks good. And then 20 to 40, we add 20. 40 to 50, we add 10. And 50 to 55, we only add 5. So same problem as part B. This is also not a linear function. Alright, for the same reasons, we don't have equal changes in the h of x values. Alright, so what can the slope tell us about a function? The slope can actually tell us a lot of things. Okay, so a positive slope means that the function is increasing. Alright, so a little graph here, x and y. A positive slope is something like this. Okay? A negative slope means that the function, well, if positive meant it was increasing, negative means it is decreasing. Okay, so on our x and y axes, this is what a negative slope looks like. Okay? A large slope means, or I'm going to say a large magnitude. And magnitude just means positive or negative. Okay? So a large magnitude, in our cases here. So a large magnitude of slope means that the function is increasing or decreasing quickly. Alright, so if it's negative, it's decreasing. If it's positive, it's increasing. But if it's large in magnitude or in absolute value, it's doing whatever it's doing very quickly. So what I mean by that, alright, this is the positive version, and this one over here is the negative version. Okay, this would be a very steep, a very large positive slope. Okay, and similarly, this would be a very large negative slope. Alright. A small slope, again in magnitude. So a small slope means that it's increasing or decreasing slowly. Alright, that the function is either increasing or, my pen is loading, a small slope means that the function is increasing or decreasing again slowly. Alright, so again, I'll show a positive and negative version. So this is the positive, this is the negative. It'd be a very small slope, so almost flat. Okay, similar thing with the negative slope, almost flat. Okay, so whatever it's doing, increasing or decreasing, it's doing it very slowly. It's taking a long time to do that. Okay, a zero slope means that the function is not changing. So that means it is not increasing or decreasing. Alright, and a zero slope is a horizontal line. Alright, so if you are asked to find or draw a horizontal line, then you're going to immediately know that the slope must be 0. And if you're given a slope of 0 and asked to draw a graph, you know it has to be a horizontal line. Okay? And no slope or an undefined slope actually is a vertical line. So again, this is x and y, and an undefined slope would be something like this. Okay, and if you need help remembering a zero slope versus an undefined slope, so a zero slope, if you think about skiing, I'll make this a little bit bigger over here. This is our zero slope, alright, and if you are skiing, alright, so here's a person on some skis with some ski poles, alright, beautiful drawing. It's rough to, push yourself along on a flat surface, but you can, right? You can ski on a zero slope, okay? If you're trying to ski on this slope over here, okay, it's not going to work out very well. Alright, you're just going to plummet straight down. Okay, so you can't ski. I'll say can ski with 2 eyes? I don't know, we'll leave it as 1 eye. And this is you can't ski. So hopefully that's how it helped me to remember which one was a zero slope and which one was an undefined slope. Alright. So let's go ahead and look at example number 2. So for each of the following situations, we need to find and interpret the slope and the vertical intercept. Okay, so our first part A, an icicle grows according to the formula given here, where t is the time in hours since the first measurement was taken, and w of t is the width of the icicle in centimeters. Alright, so we have our formula that's given to us, w of t, so w of t is equal to 0.2 t plus 0.15. Okay, and this section is all about linear functions. Alright, so maybe if you think about this for a second, does it kind of look like y equals mx plus b? Well, what if we change x for t? If we have y is equal to mt plus b. Are we getting a little bit closer? Okay, if we look at this formula here and this formula here, we want to try to match some parts. Okay, so what are we multiplying by t over in our formula that we were given? Well, we're multiplying by 0.2. So, based on our formula, our slope is our m value, and that is 0.2. Okay? And B is our y-intercept, remember? And that is where we are adding our 0.15. Okay, so we found the intercept and the slope, but now we need to interpret them. What do these values mean in our problem here with the icicle growing? Okay, well, earlier we discussed slope is the rate of change, right? Rate of change. Okay, we discussed that slope was the rate of change. Also, this slope is positive. And earlier we made a note that a positive slope meant that whatever was happening was increasing or getting bigger. Well, if we double check our problem, we have an icicle that is growing. So it makes sense that our slope is positive because something is growing. It is getting bigger. Okay, so that checks out. So the slope is the rate of change. Also, our slope is positive, so we know something is increasing. So we know the size is increasing. How fast is it increasing? Is 0.2 a large number or a small number? Well, it does matter what you're talking about, but generally speaking, 0.2 seems like a fairly small number. So we can say, so we know the size is increasing slowly. Okay. All right, because it's only increasing 0.2 per hour. Okay. And 0.2 centimeters per hour. So pretty slowly. Okay, so we've now found and interpreted the slope. Okay, and let's see, let's interpret this y-intercept here. Okay, so the y-intercept is 0.15. What happens when t is equal to 0? If we're looking at our original equation, if t is 0, anything times 0 is 0, right? It could be 1,500 times 0. Well, that's 0. Okay, so we have 0.2 times if t was 0, so that would go away, and we'd only be left with 0.15. So I'm going to write this down. At t is equal to 0, which means no time has passed yet. We're at the very beginning. Okay, at t is equal to 0, our w of t is 0.15. And what does the w mean? W is the width of the icicle. Okay, so at the very beginning of our measurement process, the width of the icicle is 0.15 centimeters. So our y-intercept here at 0.15, this is the starting size. Is the starting, if we want to be specific, width of the icicle in centimeters. Okay, so we found the starting width of the icicle. That was our intercept, and we found that it is growing very slowly according to our slope. So we have now found and interpreted both the slope and the vertical intercept in this problem. All right, so now let's do it again for part B. So now we have an international travel data plan. And the cell phone provider charges its customers according to this formula. Okay? N is the number of megabytes of international data used, and C of N is the total charge in dollars for 1 month of international service. So again, we need to find and interpret both the slope and the intercept. Alright, take C of n. I always like to rewrite equations just so they're right in front of me. And sometimes when it's in my own handwriting, it makes more sense in my brain. It might be a neat thing for you to try. Alright, so we have C of n is equal to 10 plus 2.05n. Alright, so if we write down our equation of a line, y is equal to mx plus b, again, we're just trying to see what values line up with an equation that we already know. Okay, well, first of all, we don't have an x, we have n's, right? That's totally fine. Whoa, pen's going wild. Y is equal to mn plus b. Okay. So let's see, what's the only thing that's different now? Well, they're in a different order, right? But addition is what we call commutative, right? So we can switch around this order and nothing's going to change. So 10 plus 2.05 times n is the exact same thing as saying 2.05 times n plus 10. Alright, we can just switch around the order there. And now it looks a lot more like our formula over here. So let's go ahead and line this up. Our slope is what we're multiplying by n. So it looks like our slope is 2.05. Okay. And our intercept is what we are adding or subtracting. It could be a negative number. Okay. B is equal to 10. So that's our y-intercept and our slope. But now again, we need to interpret what these values mean given this situation. Alright, so let's look at the slope again. And let's read this problem one more time. So we have, it's a data plan for a cell phone, right? And so we have to have a base cost, and then we keep adding money, or adding a charge, okay, depending on the amount of megabytes of data used. Okay, so it needs to keep adding money per megabyte. Okay, so we have this 2.05. Well, we know that our slope is the rate of change. Okay, again, this slope is positive. So that means we have something that is increasing. Okay, and 2.05 is a lot bigger than our 0.2 number earlier. So I'd say this is increasing kind of quickly. Alright, it's a kind of a large slope. So we can say this is increasing quickly. Depending on how quickly you really go through megabytes of data, right? Okay, so that's our interpretation of slope. And our interpretation for the y-intercept, well, again, y-intercept, let's see, the y-intercept occurs, need two C's, there we go, occurs when our dependent variable, where n is equal to 0. Okay, so if you use no extra megabytes of international data, okay, then they're still going to charge you $10, even though you have not used any extra megabytes of international data. Okay, so the B is equal to 10. This is the base price. of the data plan when no megabytes of international data are used. Okay? So we found our slope, we found our y-intercept, and we determined that you're at least going to be charged $10 a month. That's the base price. That was the y-intercept. And the slope is fairly large. So if you keep using megabytes of international data, your price is going to increase fairly quickly. Okay? And that wraps up part B for this example. So, earlier, we discussed one of the types of forms that a linear function could be written in. We discussed the slope-intercept form. Alright, and that was our y is equal to mx plus b, because we use a slope and we use an intercept, right? Okay, well, we have another form. Another form is called the point slope formula. Alright, and if you're thinking it's named for a similar reason, you would be correct. We need both a point and a slope in order to put together this formula. Alright, and the formula is y minus y sub 0, which I'm going to read as y naught, okay, is equal to m, which is our slope again, x minus x naught. Make that a better 0. X naught. There we go. Okay, and so again, this is our slope. And this y naught and x naught, they are going to come from the point. So whatever point we're using, which will be x naught, y naught, okay, we just plug in those values. And the other x and y we leave alone in the formula, okay? So this is our point slope formula. Okay. So how could we use this? Sometimes you'll be given 2 points. Sometimes you will be given 2 points and asked to find the equation of the line. Okay, so if we're given 2 points, we're not given a slope immediately, right? So the first thing to do, the first step, is to find the slope. Alright, which we remember our slope is, let's see, a bigger y value minus a smaller y value over a bigger x value minus a smaller x value. Okay, and remember, we can have a negative slope, that's okay. We can have a fraction as a slope, we don't always need decimals, it's fine. Okay, so we could use this to find our slope, and then you just pick one of the points. So you pick one of the 2 points that you're given and use it as the x naught, y naught point that I was just mentioning a moment ago. In the point slope formula. Alright, so this is what we are going to do in the next example. Alright, and this next example gives us a few extra steps in here as well that we got to figure out. Alright, so example 3, find an equation for the line h, alright, that is this line right here, which passes through two indicated points on the graph of y is equal to negative x squared plus 4. Alright, so that's this upside down parabola that's happening here. Okay? So you might say, well, wait a second, we're not given 2 points. Okay? And you would be correct. We are not explicitly given 2 points. However, we are able to figure them out from the information we have been given. Okay? So again, our parabola is this y is equal to negative x squared plus 4. Okay? And one bit of information we are given is that this x value is negative 1. Alright, so what we're going to do is try to find these 2 points, and then once we have 2 points, we can come up with the equation of the line, right? So, I'm going to put this here and this here. We want to find these points, and we know that x is negative 1. Okay, so how do we find the y value? Well, we know that it's also, this y value is shared with the parabola. Okay, so we want to know the y value where x is equal to negative 1. So what we're going to do is plug x is equal to negative 1 into our equation of the parabola. Alright, so we get y is equal to negative. Always be extra careful when dealing with negatives, alright? So that's why I put this negative 1 in parentheses before I raised it to the second power, plus 4. Okay, so we have y is equal to, I'm going to leave this first negative out here, but negative 1 squared becomes positive 1, right? Plus 4. So then I can go ahead and drop these parentheses around the 1 and just get negative 1 plus 4. So we get y is equal to 3. So we wanted to know what is the y value when x is equal to negative 1, and we get y is equal to positive 3. Alright? And so there's not a whole bunch of numbers labeled on this graph, so maybe we can't be super sure about it, but it makes sense that it's positive, right? Because it's above the x-axis. Okay? If we got a negative number, that would say my y value had to be down here somewhere, and that wouldn't make any sense, right? So it's always good to make sure that everything kind of checks out. There's no red flags there. Okay, so guess what? We have a point. Alright, now we need to find our second point. And our second point, they didn't help us out by giving us an x value. Okay, what can you determine from this point though, based on the graph? Can you determine that the point is one of the zeros of the function? A zero of the function? Or a horizontal intercept? And what does that mean? So if the y-intercept, the vertical intercept, happens when x is 0, that must mean that the horizontal intercept, the x-intercept, must happen when y is equal to 0. And that makes sense because 0 is right here, right? This is the 0 line for y. The x-axis, along the whole x-axis, y is 0. Okay, so we have y is equal to 0, and we want to find, okay, so we want to know the x value where y is equal to 0. Well, we're going to do the exact same thing as we did a moment ago to find the y value, but now we're looking for the x value instead. Alright, so instead of saying y equals, I'm going to say 0 equals. So 0 equals negative x squared plus 4. Alright. Then I'm going to add x squared to both sides. So now I get x squared is equal to 4. And how do we undo a square? Well, we undo a square by taking its square root. Alright, so I need to take the square root of both sides, because remember it's an equation. Whatever we do to one side, we have to do to the other. So the square root and the square cancel each other out. And what is the square root of 4? So what times itself gives us 4? Well, that would be 2. But what about negative 2? Alright, so x is equal to positive 2, or I'm going to say and x is equal to negative 2. Alright, if you think about it, negative 2 times negative 2, well, the negatives cancel each other out, so that will be positive 4. So we have 2 answers for this problem. Well, if we come back and look at our parabola, and we see that we have y is equal to 0 at 2 places. So that makes sense that we have 2 answers, okay? But we only need one of these answers. So we need to pick which answer do we need. Well, we're looking for the positive x because we are to the right of the y-axis. So we need the positive option, and so that's why we are going to choose x is equal to 2 because we need the positive option for this problem. Okay, so when y is equal to 0, x is equal to 2. So now we can fill in this blank here. Well, would you look at that? We now have 2 points that our line goes through. Alright, so I know that was a lot of work just to get to those 2 points, and now we're not even done yet. We now have to use those 2 points to come up with the equation of the line. Alright, so I'm going to rewrite my points down here. So we have negative 1 and 3, positive 2 and 0. Those are our 2 points. Alright, and let's call this x1, x2, x1, y1, and this is x2, y2. Okay? And that's going to be helpful because we need to find the slope, right? Find the slope. Alright, and remember, we have our difference quotient. So it's our y2 minus y1 over x2 minus x1. And it doesn't matter which set you choose to be 1 and which set you choose to be 2. Okay, all that matters is your x sub 2 and your y sub 2 are together, and your x sub 1 and your y sub 1 are together. So that's why I like to write it down to help me keep it straight. Okay, so I need my y sub 2, which is 0, minus my y sub 1, which is 3. It's okay if 0 is technically smaller. Alright, like I said, it doesn't matter. So then we have our x sub 2, which is 2. Alright, minus x sub 1, which is negative 1. And we see I'm using parentheses here again to be super careful with my negatives. So 0 minus 3, well, that's just negative 3. And 2 minus a negative 1, well, these will actually cancel each other out and become positives. Alright, so that's 2 plus 1. Well, that's positive 3. So negative 3 over positive 3, well, that's just negative 1, right? So our slope is negative 1. Alright, well, we have a slope and we have 2 points. So we have more than enough now to use our point slope formula. Alright, so again, remember that looks like y minus, you could say y1, y2 is equal to our slope times x minus x naught. Alright, let's go ahead and pick our x1 and y1s here. We're going to use this point. Okay? So we're going to use y minus our y point in our first point here. So that is 3. So y minus 3 is equal to our slope, which we just calculated to be negative 1. So negative 1 times x minus our x, which was in our point that we chose, which is negative 1. So again, I'm using extra parentheses there. Alright, so technically done at this step. I'm going to write that out. Technically done. Alright, but we're going to keep going because I want to prove to you that this is the same as y is equal to mx plus b. Alright? So I'm just going to do a little bit of algebra here to move things around. So I have y minus 3, negative 1 times x plus 1, canceling out those negatives there. So now I'm going to distribute our negative 1 in. So I'll get negative x minus 1 now. There we go. And now I'm going to add 3 to both sides. So I'll get y is equal to negative x minus 1 plus 3. So we get y is equal to negative x plus 2. And does this look a little bit more like y is equal to mx plus b? Alright, with m is equal to negative 1. We don't need to write 1 here because it's redundant, right? You can if you want, you wouldn't be wrong, but it's just unnecessary. Just the negative is all that we need. Okay? So that's just proving to you that these two formulas give you the same thing. Again, but you could technically stop here. Alright. So that was example number 3. Moving on to number 4. We have this crazy graph here with a bunch of different functions on it. Okay? And several parts to this problem where it's just asking us general questions about each of these functions. Okay. So, which function, I'm going to go ahead and no, we'll leave it as it is. Which function has a negative slope? Well, remember, a negative slope, if this is our y and x axes, a negative slope is one that's like this. Okay, it could be a steep negative slope or a gradual negative slope. Okay, but it has to be coming from this direction. So, if we take a look at our graph over here, the only function that seems to have a negative slope is this h of x. Okay? So we're going to say h of x has the negative slope. Okay, so for part B, it asks what function has the highest magnitude slope. So remember, that could be positive or negative, but it's just a very steep slope, right? And a steep slope, I just drew an example. This would be a positive steep slope, positive, and this would be a negative steep slope. Okay, so based on that pretty bad drawing over there, which of the functions in our graph matches the best? Well, to me, it looks like j of x seems to have a pretty steep positive slope, right? So we're going to say this is j of x. Okay. Part C, which function has a slope of 0? Well, remember we looked at that earlier with the skiing, okay? And a slope of 0, that was the one that was kind of annoying and hard to ski on, but you still could. Remember? So that's one of these flat guys here, right? So if we're looking for a horizontal line, well, g of x is our only option. All right, so g of x has a slope of 0. So part D asks which function has the greatest vertical intercept. And we remember that the vertical intercept is the y-intercept, okay? And that's where the function crosses the y-axis, okay? So this is our y-axis. And we want to see what function seems to cross it at the highest point. And it looks to be right here is the highest point that anything crosses it. And, well, that's our g of x again. All right. So g of x has the highest vertical intercept. And then we are asked in part E, what function has the smallest vertical intercept? And so that's the lowest that a function crosses the value on the y-axis. And so again, it looks like it's this one, which is our f of x. All right. Our f of x. So that graph looked a little bit crazy and overwhelming, right? But it was some fairly simple questions if we just looked one at a time. Okay, so example 5. How can you tell if two lines intersect once, indefinitely, or not at all? In particular, what can be said about the slopes in each of the following situations? Fill out the chart below and draw pictures of each scenario. So we need to fill out this chart whether we think these two lines described in each scenario are going to touch each other once, infinitely many times, or not at all. All right, and we're going to draw pictures as we do this to help read the scenario. All right, so our very first scenario, same slope, different intercept. Okay, so let's draw a few examples of what this could be. Pick whatever slope you like. All right, this is just our typical y equals x line. Okay, and if I drew it properly, it would have a y-intercept of 0. Okay? Well, we need the same slope different y-intercepts. So you can go up or down, wherever you want, but it needs to have the same slope. And same slope, I'm going to write this down, means lines are parallel. Parallel. So it could be this line. This has a different y-intercept. It's a little bit higher, right? It could be this line. This intercept's a little bit lower. It could be this line way down here. All right, same slope, different intercept. And these are going to keep going on and on and on forever, and ever and ever and ever. Do we think any of these lines are ever going to touch? All right, maybe if I drew them perfectly, it would be a little bit more obvious. But because they're parallel lines never touch. So, we can mark the 0 box for the same slope, different y-intercepts. Okay? So, now we're going to look at same slope, same intercept. What does that mean? So same slope and same intercept. Okay? So again, we'll leave our y is equal to x here as our typical line. I'm going to take yellow now. So same slope, same intercept. Same slope, same intercept. Well, is that not just the exact same line? What about here? All right, so this line, again, would be straighter, and same slope, same intercept. Purple's going right on top of the yellow there. All right, so the black and the yellow, the purple and the yellow, both options for same slope, same intercept. Well, those never stop touching each other, right? They don't just touch each other once. They are infinitely intersecting. Okay? So they are intersecting everywhere. It's the same line. You just put another one on top of it. All right, so we're going to have infinite number of intersections. If it's the same slope and the same intercept, that means it's the same line. All right, now how about a different slope, different intercept? Different slope, different intercept. Okay, so let's do a positive slope, and let's go ahead and do a negative slope, but a different intercept. Let's choose this point. Hey, look at that. We intersect. All right, well that's one intersection. If we keep going forever and ever and ever in all 4 directions, are we ever going to hit each other again? No. So a line can only intersect, 2 lines can only intersect 0 times, 1 time, or infinitely many times if it's the same line. But there is no possible way a line can intersect 2, 3, 4 times. Okay? That would be something other than a line if it did that. All right, so a same slope, different y-intercept. Let's do it again. Let's do a different one. All right, so, or different slope, different y-intercept. Let's do another positive one. All right, let's do the same intercept as before, but another positive slope. Well, would you look at that? We intersected again. Okay, so different slope, different y-intercept. We're going to intersect once. All right. So now we have different slope and same intercept. Think about this for 2 seconds. What do you think's going to happen? Different slope, same same y-intercept, well, it's got to go through the exact same intercept, right? So of course it's going to touch at exactly that intercept. All right, what about this direction? Different slope, same intercept. Of course it's going to intersect, so this will also intersect. All right, so we have now successfully filled out this chart. All right, so example 6, a bunch of little small problems all together. Just asks us some general equations, just as kind of a summary of what we've captured today. So the general point slope formula for an equation, well, that is our y minus y naught is equal to m times x minus x naught. And it asks us to label all of the points. So m is the slope, and the y naught and the x naught come from the point, whichever point you choose to make your x naught and your y naught. Okay, the general slope-intercept form, well, that's our y is equal to mx plus b. Again, we gotta label all the parts, so m is the slope, and b is the intercept. Alright, the general slope formula, let's go ahead and write that as our difference quotient. Alright, but if we remember, it's the change in y over the change in x. And so we have y2 minus y1 over x2 minus x1. And that's our difference quotient. So the slope-intercept equation, but specifically for the line with a slope of m is equal to negative 4 and a y-intercept at this point, 0 and 3 over 2. Well, our slope-intercept form, that's our y is equal to mx plus b. Here we are given a slope of negative 4, so we have negative 4 times x. And then our point here, this is x, this is y. Whoa, pen went wild. This is y. So our y, or our b value, is plus 3/2. And there we have it. That is our equation of the line for a slope with negative 4 and a y-intercept of 3 over 2. Alright, how about an equation for the horizontal line passing through a point? Okay, we were given a point. That's exciting. We were not given a second point, though. So how can we find the slope? Does it tell us anything about the slope? Indirectly it does, because it says we have a horizontal line. And what does the horizontal line mean? Our slope is 0 on a horizontal line. Alright, so let's take a look. This is our x and y axes. This is negative 4, and somewhere over here is 7.3. So, a line that goes through one point but with a slope of 0, well, it's just the line y is equal to 7.3. It doesn't matter what x value you're at. X is negative 2, x is positive 3. You're always going to have a y value of 7.3. So y is equal to 7.3 is your equation of this line. Okay, so for f, we have an vertical line passing through a point. So again, we're given a point, and we're not given any information about the slope directly, but we're told we have a vertical line. And that's the one where if you try to ski on it, you're not going to be able to. You're just going to fall down. So, we have a vertical line. This is x and y. And this is x is negative 13 all the way over here. And y is 5. So, it goes through this point. Okay. And it's a vertical line, so if that was super straight, this would be our line here. So in this case, it doesn't matter what y is doing, you're always going to have the same x value. So x is equal to negative 13. That is our equation of our line. We don't have a slope here. It's an undefined slope. Okay? So we have x is equal to negative 13. And that is your equation of this vertical line. Alright, so part G is we want to know the linear function h such that h of 1 is 4 and h of negative 2 is 13. So how are we going to go about this exactly? We need some points, don't we? How are we going to find some points based on what we are given? Well, if we think back to our first lecture, what is a function? We talked about input and output. Input is normally x, output is normally y. So if we're looking here as what we are given, well, we have some inputs. We have 1, negative 2, these are some inputs. And we have 4 and 13, these are some outputs. So we can group these together. So our input, 1, gives us 4. And our input, negative 2, gives us 13. And this is our x and y values. Let's see, this is x2, y2, and this is x1, y1. So now we have 2 points. We can use this to find the slope, and then we can use our point slope. Okay, so our slope, that's our m value, and we need our y2 minus our y1 over our x2, which is negative 2, minus our x1, which is 1. So we have 13 minus 4, so that's 9, over negative 2 minus 1, well, that's negative 3. And 3 goes into 9 3 times, so we end up with negative 3 as our slope. Okay, so now we have a slope, and we have whichever point you want to pick out of these 2 points. So we're going to use the point slope formula. Alright, we have our y minus whichever y you want to use. Let's go ahead and use this 1 and 4 point. I normally like to pick the smaller numbers because it makes computation a little bit easier, but you can pick either point, it will work. Alright, so y minus 4 is equal to our slope, which is negative 3, and then x minus 1. And I'm just going to go ahead and leave it like that. And finally, part H asks us to find the intersection of the line y is equal to 2 and the line x is equal to negative 3/4. Well, according to a little bit of the work we've done previously, y is equal to 2. What kind of line is this going to be? Does it have a slope? This is going to be a horizontal line. So the slope is 0. Alright, it technically has a slope, right? It's just the slope is 0. And how about x is equal to negative 3/4? Well, that is a vertical line. It actually doesn't have a slope. It's completely undefined, right? So where do these two lines meet? So if this is x and y, we have y is equal to 2. Y is equal to 2. And x is negative 3/4. X is negative 3/4. And that is a vertical line. And this point right there is where they intersect. And it's exactly negative 3/4 and 2. That is the intersection of those two lines. Alright, so last problem for today, problem number 7, is just matching some equations to the graphs. Alright, I'm going to use a different color here. Let's use this kind of fuchsia-y color, so it's a little easier to see with all these lines going around. So, let's see, maybe we want some strategy to what we are doing here. How about let's look at these two graphs first and try to find their corresponding equations. Why did I single out these two graphs? Well, they both have negative slopes, right? Both negative slope. So, I want to look for the equations above that have negative slopes. And our slope is what we are multiplying by x, right? So, this is a negative slope. This is a negative slope. And this is a negative slope. And those are the only two negative slopes on in our options here. Okay, so we've narrowed it down. Somehow we have to match these. Okay, so what is the difference between C and E? We both have y equals negative b times x. Well, one of them is plus an a and one of them is minus an a. So they moved the letters around to maybe try to confuse you, but a is our y-intercept here. Okay? Y-intercept. Sometimes we just abbreviate as int. This is the y-intercept. Okay, so a negative y-intercept means that it crosses the y-axis at a negative number, so that's below the x-axis. And a positive y-intercept means that it crosses it higher. So we have a positive y-intercept over here, and we see that this line is crossing the y-axis above the x-axis, so where all of the y values are positive. So we're going to go ahead and match E to 5, 6, this is 7. Okay, and that leaves us with C and 6. So the negative y-intercept crosses the x or the y-axis below the x-axis. All right, so in the negative values. All right, so we just knocked 2 out of here. Let's see what else we can knock out fairly quickly. Okay, maybe let's look at the zero slope or the no slope, the undefined slope versions. So maybe this one and this one. Okay, we know, let's look at the vertical line. We know that a vertical line looks something like x is equal to some number, right? It doesn't matter what number it is. It could be 17. It could be negative 32. Okay? It could be 0.1. Some vertical line. Okay? Do any of the above equations match this formula? X is equal to something. Well, the only possible option is D. x is equal to 2 times b. Now b is just some positive number. So 2 times some other number is just a number, right? And that's what we were looking for. X is equal to a number. So we can go ahead and match D with 4 over here. Graph number 4. Alright, so graph number 3, the other one circled in pink, well, that's a horizontal line. And we know that horizontal lines have a slope of 0, and it looks like y is equal to, again, some number, right? So we take a look at the rest of our equations that we have left. We only have 4 left. And we say, which one matches best with y equals a number? Well, A looks promising at first, but then we realize there's an x involved in there, right? So we can't have an x involved. We just need a number. B, that's not helpful either. There's an x involved. How about G? Y is equal to A plus B. Well, A is just some number, and B is also just some number. So A plus B is just going to give us some number, right? So that matches best with y is equal to some number. So we are going to match G with graph number 3. Alright, we have 3 left. What do we have here? So we have 3 graphs that have a positive intercept. Let's write this down, actually. What do we see about all of these? Let's use this green. Alright, so here we have a positive, I won't use that, I'll say positive y-intercept, right? Here we have a negative y-intercept. And here we have a 0 y-intercept. It crosses the y-axis at 0. So that should help us narrow down which equations best fit with these graphs. Alright, so let's look at the positive one first. We need a plus some number at the end. Alright, so for B, we have y is equal to ax plus b. So a is our slope times x, and b is our positive y-intercept. So B is going to match with graph number 2. Alright, so then F is our same slope, but now with a negative intercept. So we're going to go ahead, and match F with 5. And then the only one left is y is equal to a over 2 times x. And we need to match that one with graph number 1. And that makes sense because we said graph number 1 has a 0 intercept. So we could technically write plus 0 over here and nothing would change, right? So that's where we get our 0 intercept from. So we have now completed our last problem for today. Do not forget to take the comprehension quiz, and I will see you in the next lecture.